cryptography. We are very happy to have Rachel Cummings from Columbia, who will talk about differential privacy. Thank you.
Cool, thank you. So I'm thrilled being here. I'm thrilled also to have moved onto the East Coast corridor. It's so easy now. I'm obsessed. Yeah. So I'll be talking today about a differential privacy for the task of doing an imbalanced learning, which I will define on my next slide. And I feel like this is sort of not a typical differential privacy talk. I mean, it kind of is, but I feel like a lot of talks I give are of the form, here is a problem and we want to solve it privately. Here is an algorithm that will do that. And in this talk, well, that will be a part of it. That's sort of not the main point. And the main point is almost what goes wrong when you think you're doing privacy, but you do it wrong. So that's kind of what this talk is. I should mention this is joint work with my two students, Julia, who is a very freshly minted PhD, and Itan, who is a senior and is applying to grad school. So maybe he will come. Who knows? And my colleague Mark. So on the task of doing imbalanced learning is a task where you want to do something with a data set. In particular, we're thinking of binary classification of some data. We have a very large class and a very, very small class. So examples include Twitter spam, although I realized in the past couple of weeks, this question of what the percent of that is a bot is a highly politicized question. So I don't entirely know 3% or not. But you can also think about doing fraud analysis of some transactions, detecting diseases where you have, for the most part, things are uninteresting, and then you have a very small but also very important class. And let's say you have some a training data, and you want to train a binary classifier on this data. And the challenge is you don't have enough minority data to kind of do it in the normal way of just apply a classifier learner and be done, because a really good classifier is just to say everything is not spam. No one has a disease, and this will be correct with high probability, but you're somehow missing this most important part, which is you want to identify in particular this smaller group. And I won't sort of motivate the need for privacy here, but I will just say in these examples, people's internet behavior, financial transactions, healthcare data, you're thinking about a case where you want privacy. And so because I am me, when I say privacy, what I actually mean is a differential privacy. So if you haven't seen it before, I have 3 quick slides about it. And in pictures, it looks like this. Imagine if I have a database feed, and this database contains data coming from a multiple people, and then you plug that into your favorite randomized algorithm. Well, then that will give you out a PDF curve of the likelihood of a particular output of this algorithm instantiated on this particular database. And our privacy guarantee considers, what if I change one person's data? Say that I change Alice into being Javier, and I then plug in this new database that is the same except for one person's data into my same randomized algorithm, and it'll get out a new curve. And the goal, privacy-wise, is to say that this ratio is going to be bounded point-wise everywhere along this axis. What does it actually mean? Or what does that mean privacy? Well, so you can imagine if an adversary observed this a particular output, and they then try to infer that I observed this output because of Alice, because of Javier. Well, in that case, no real meaningful inferences could be made aside from the amount allowed by this bound on the ratio. And so this is why it is privacy. And in fact, it holds for all pairs of databases a la Javier, and for all possible like things on this x-axis, and so that's like for all possible things might be output as a result of the analysis. So a map that says this, so we'll have an algorithm M, the map from a kind of like database of size N, into some arbitrary range R, and we'll say is parameterized epsilon delta differentially private. But it's the case for pairs of neighboring databases that are the same except for one first data, and for all possible things I may produce as a result of the analysis, I'm going to produce that thing that's about the same probability under these two different databases. And so you can think of this as kind of like the world with you and the world without you and so on. And so if you ignore this like a delta for a second, then you get back this bound on the ratios. And you'll see that our epsilon is the exponent. So it's not as kind of like natural of a way to like parameterize as you might think, but that's what it is. And then you have this like a delta term, and this allows for a small amount of additive slack. You can think of it intuitively as being like there's a delta chance that your epsilon bound fails to uphold. But if you want to say that precisely, it really matters what is the order of the quantifiers before you make that argument precise. And so I always hesitate saying it because it is true for some formalizations and false under others, but you can intuitively do that. And we now have these things used in practice kind of everywhere that you imagine, every big tech company and a lot of smaller ones. There's a highly public, albeit controversial, use in the government and so on. And it's kind of addressing the point if you want to learn global things about the population without learning things about the individual. And so the canonical example is saying I want to learn if there's a causal link between smoking and lung cancer, but they don't want to learn about your So a couple properties that are going to be important in our talk, and they're also what make a differential privacy a very nice notion. So then the first one is called post-processing, and this means that if I perform anything differentially private, and then I do anything afterwards to it, it's going to maintain the same privacy guarantee. And this is nice because you can think of this thing happening later as being an adversary trying to break your privacy guarantee, and so we prove, or not we, but they prove for any adversary, information theoretically, computationally unbounded, and regardless of the adversary's auxiliary information, I cannot reverse engineer privacy. And so this is absolutely what you want in a privacy notion. Now it's going to be important in our talk is this is post-processing. And so this is saying if I do privacy first and then I do something else, it's still private. Today we're going to be talking about the reverse. If I do a non-private thing first and then private later, we'll see how this importantly doesn't hold that. One more thing that is very nice about a differential private algorithm is there privacy guarantees degrade gracefully as you perform additional analyses on the same data set. And so what I have right here is the one that is the completeness to state, but it's not the most tight bound. And it basically says if you do k things, each of them being an epsilon dp, it will give you in total k epsilon dp. It's great. You can improve it to a square root k epsilon. You have some constants and log factors in a delta. Questions about this before we talk about the actual content? I will say that kind of like one way in which these two things are very nice in terms of doing algorithmic design is that it lets you do like modular algorithm design, meaning that if you want to build something complex, you don't have to think about privacy from scratch, but rather you can think about the number of like very simple private building blocks, compose them, post-process them in some larger like a complicated. So back to our task of doing like a private imbalance learning. So we'll start with talking about kind of like what is known before privacy, because of course this is not a new problem. It's been thought about in the stats community for a long time. And then I'll talk about what are some challenges as you just try and like plug this into a like DP learning pipeline. And I'll come back and talk about like how can we inject privacy here. And then finally, I will show you some plots. I know this is a theory seminar, so we don't have like very many plots because I know this is not the crowd. And of course, if you have any questions, anytime, please ask. So let's start with kind of like how has this problem been like thought of in the past and years and is large in the stats community. And you basically think of it in this pipeline. How you have your data, and then you do something to it to address the fact that it's imbalanced, hopefully fix that. And then you're gonna apply your favorite like learning algorithm that will produce a classifier for you. So it's simple. And this means we already know how to do this well, and we're going to be thinking about this step in particular. And I'll start by saying, why do you want this? Why can't you just like skip this step entirely and be like, I'm just gonna like plug it into my algorithm? And I kind of mentioned this on my first slide, which is that we were really thinking about cases where the minority class is very small, it's too small to do nothing. So you have like 300 examples. This like isn't enough to do interesting things with for most interesting tasks. And also, if we're thinking about like plugging this into privacy, you've seen like our private algorithms have a disproportionate impact on minority groups in a few different ways. First of all, they're going to give like a higher loss on the accuracy group, and then they're also going to kind of like amplify like existing bias and unfairness. And from a privacy perspective, this is actually unsurprising. And this is like because we're trying to hide the impact of kind of one person or small groups in my data set, that if I have a small group and it is small, then like by definition, differential privacy is going to hide its impact. And so we can't really expect to have like an accurate prediction for small groups because that is in like direct opposition to the privacy goals. But if you were to first like amplify the size of your smaller group, then you can do things privately. So in some sense, it kind of like ignores the bias. So an example, I think this arises in school admissions and loan applications, which is like slightly different. But like for example, if you want to take into account the fact that your minority class has received historical inaccuracies, inequalities, and your training data might be biased because of that, and you want to fix it. For example, by requiring fairness here. And if you do a private classifier, we'll have a hard time correcting for that. So you might want to say, for example, for kids coming out of a specific neighborhood, I want to use maybe a lower threshold of their SAT scores for admission, and then you run into the same problems where the privacy prevents you from even learning that in the training process.
So it's unmodified, so it just doesn't let you learn.
Yeah. Yeah, so how this is commonly done, one approach is what's called like undersampling. How you just reduce the size of your minority class. So you have a big class and a small class, you can make big class smaller, and then they'll be the same size. However, this is sort of obviously the wrong thing to do, because you have a bunch of data, it's pretty valuable, and you're going to throw away most of it. So this is not a great idea. But at least it is an easy algorithmically to do, even if it's not the most wise thing. And the other version is to kind of oversample minority class. And so in this way, you want to do some kind of process here. You amplify the size of your minority class. And an easy way is to make k copies of each minority example. But it turns out you're going to be kind of overfitting there, and so that isn't the best thing to do. And the current state of the art in this space is what's called SMOTE. It stands for a synthetic minority oversampling technique. And in pictures, it looks like this. So you have some majority data, minority data, and it's going to add points that are Cummings combination of your minority points, and then you have a bigger minority class. And the goal, if you look at this picture, is you want to kind of fill in this space with more points, so that then it can be plugged into your downstream. So in words, it does this. So it kind of goes through, and it repeatedly picks an example of minority class, and it then finds that points k nearest minority neighbors, and then a random picks a neighbor, and it then picks a random Cummings combination between at that point and its neighbor. And so doing this, it kind of amplifies machine learning models' ability to kind of recognize minority class samples without really changing where the minority class lives, because you will only have points in a cluster of kind of other points. An algorithm, it says this. So you for n time, you're going to go through and you're going to compute the k nearest neighbors at each point. And you're then going to go through, randomly choose a neighbor, disable a point, uniformly random, then take that convex combination, and then we'll add z into this set, and we have this. So okay, it's pretty simple.
So I'm not that familiar with this literature, but is there kind of a broader agenda of generative adversarial synthesis? Just train another algorithm to write with your spam, or to produce instances and then try to learn which ones are real and which ones are not?
Not so much in this space. I mean, in general, in the broader space of doing kind of synthetic data generation, there's a ton of work in that space. I think this is a unique case where you don't have enough training data to do that. And then the question is kind of what can you do? And surprisingly, stuff that was done, this paper is from 2002, and so surprisingly, or perhaps not, things that work best in this application tend to be ones from before the days of big data or so on. Because again, think of one of our training sets, we had 200 minority points. And it's just you can't really train again with that. Yeah. And I think there's an interesting broader point here that I think relates to the kind of synthetic data generation work. Whereas I feel a lot of that is very algorithmically interesting and complex, and the performance is great. And in some sense, this is doing something that's not very clever. I'm sorry if like if this is recorded like on the internet, authors will be mad. But it's not doing something very clever and very advanced. But at the same time, you're kind of like a bar for what success looks like is much lower here than it is in kind of other applications. You just want to like make more points in this area, and you're not trying to like pretend like they are real points and that they like structurally match. But if you're just trying to learn a classifier, then you just want more weight over here without like overfitting to a few of the outliers. I don't quite know how to formalize them, but I think there's like something interesting to be said.
Suppose it's about diseases, and I don't have too many people with the same disease. What am I trying to learn about the genes that cause the disease, or am I trying to, because it's like they're labeled.
Yeah.
So I'm trying to learn something else about them.
Yeah. So in fact, like on this arose at a project I had with like a JP Morgan, and they had like two particular data sets. One is about fraud, one is about money laundering, and they had a whole list of like transactions, like the all important ones. And there was like 50 that were labeled fraud, and then 1,000 that were labeled non-fraud. And they wanted to build a fraud like a classifier. And so you have this like a train data, and you want to use it to build a like predictor. It can be applied in the future. You only you don't could observe.
Because there's like a small list that is a small set that is classified.
Yeah.
This is not over 50%. So it's basically the same.
Yeah,
It works.
It works. I mean, so we'll have more at the very end about the performance of SMOTE versus the private version. But the preview is it kind of it does work, and I think that I will hold more things to my last slide, but it does work in kind of a surprising way. I think the insight is really that we're asking very little in terms of making sure these new points look like precisely like our old points. They just have to be in the neighborhood of our old points, and that is somehow enough.
And it is just because now we took my
This-
information, you kind of put it in many other, we have adaptations of pieces of information. This is not key.
Amazing. Amazing question. Good. So in fact, this is like the old work from like 2002 without privacy. And do I think this is current? If we aren't, we should like plug it into a pipeline that will give us privacy. And so I do SMOTE as my pre-processing stuff, and then I do favorite like differentially private learner to learn a classifier, and I'm good, right? Because they've done privacy. But the problem is we're doing pre-processing instead of post-processing. And
By the way, we collaborated before the question.
yeah, good. Yes. Okay. Yeah, exactly. It's there. Yeah. And so this comes back to the point I mentioned at the beginning, which is that like a differential privacy is robust to post-processing, but not to pre-processing. And so it's not to say this is not private. You have to measure how much have I impacted this part. Because really, when I talk about privacy, I care about the mapping from the data to the classifier. And so you can't just look at this part, but you have to think about this part as a thing that may amplify influence at any point, and then it'll have a larger influence here in my classifier. So this is a thing that you really have to keep in mind, and this is kind of where I'm going with this, is you have to keep in mind how much have I amplified the influence of any one point before I plug it in. And so as a simple example, if I were to make 50 copies of each point. I would then have like a 50 epsilon if I use like epsilon DP algorithm here, and that's because like every point here is going to correspond to like 50 more points going in here, and so then I have to account for that. So, but of course, we're not just like replicating points. We're doing something a little more like complex. And so, like, how much more do I amplify each point's influence from here into here? Any questions? Okay. So now we have reached the point at the top. We have to apologize for not making full slides, and I want to do a little bit of stuff on the board. It'll be engaging. I will call that. So I'm first going to give you a horrible looking slide with the main results, and then I will do some math on the board to explain it. Yeah.
Just a quick question about this: the pre-processing versus post-processing. Is the issue because like with SMOTE you are creating more samples, and because you have more samples, then like you can't just like say that the differential privacy guarantees are the same, or are there any other issues with like pre-processing other than just like the fact that for this particular algorithm you are creating more samples than the initial data sets?
Yeah. So the main point is that you are this like a DP stack. So the guarantees of like this box alone are looking at kind of like what if I change 1 point in my input data that arrives here, and then how much can that affect outputs here? But the problem is that kind of like this is not our first data. This is, and we have to look at if I change 1 point here, how many points does that change here? And then I have to multiply that through here. So that's sort of like the main thing to like keep in mind is that if we look at this like DP algorithm alone, it is reasoning about this arrow, but we actually have to reason about this arrow. It's like pushed through this. Okay, so here's the slide that that deserves an apology. So I will tell you the main points and how to interpret it. So we first say if I first do SMOTE and then I apply any private learning algorithm to it afterward, we don't even have to think about what is the algorithm, how does it operate. But if it's just any single an epsilon DP algorithm, then the resulting process is going to have a new epsilon and a positive delta. And how will this depend on the input parameters? So first we have this kind of L thing, which is the maximum number of times any point can be a k-nearest neighbor of the points in the rest of the data. And why is this important? It's because they have a center point. I'm going to grab a k of its neighbors, and so then I'm counting influence not just of this center point, but of its neighbors. And so we have to count how many times can some point be a neighbor. Because in the worst case, maybe it's neighbors with everybody. And then you can say it will influence all the points that are made. And so we're going to use L for that now. The next thing will bound L, but for now it's just L. And also this kind of an N over K, N over N is basically asking how many times do I iterate through my data. And so maybe I pass through kind of all of my minority points 3 times, and then I stop. And so that's what this ratio is kind of how many passes through my data do we go while I'm kind of generating new points. and like k is the nearest neighbor, gamma can be 2. So that's what like all this means. How do I interpret this? So we see, so I take my original epsilon, and so we think that I'm getting epsilon, because we plugged an epsilon into my classifier, and then actually get like an epsilon times something bigger than 1 times, I'm now gonna have like a linear dependence and like a number of points that I can possibly be a neighbor with in my data set, times like the times a kind of number of times I go through my data divided by k. So this could like possibly be like a pretty large. And then we have a delta that is like even weirder, but the like the same things appears to me. And I want to point out, the goal of this is not to show how great of a privacy guarantee this is, but in fact the goal is to like point out this is a bad privacy guarantee. So we have something that is like bigger than 1, something that is possibly large, and some other factors. And in fact, we show that this L is going to be like an exponential in the dimension. And so you have something that is like a large number times something exponential indeed, admittedly a small constant, but still exponential. Yes, a lot of questions. Let me say one thing first, which is the way to interpret this is that if you don't incorporate preprocessing and you think you are getting epsilon, then you might actually be getting something that is much, much bigger than the epsilon that you think you are getting. Now questions. Yeah.
So this L thing depends on the data set, right? Like, is it the maximum for all possible data sets?
Yes. Yes, it is the like
If you define it that way, is it always the same thing? Like,
so it's a maximum over all possible data sets that you might have. And so then it is the same. It does depend on like a dimensionality and on K and the K is associated.
Following on the question about L, can we turn this into a per point trade-off? Because it seems as if when one point is eating a lot of K nearest neighbors, this should imply that other points won't be as bad somehow.
Interesting point. I have the next slide where I explain this, so maybe re-ask it again at the end of this slide, but I think that's a valid question.
So in terms of kind of what's the best we can hope for, without magic or kind of a lot of structure, L should be okay. Or like if under the best case scenario that does not include kind of tremendous tricks, is the other roughly constant times small constant times K?
So one thing is you want a worst case bound on L, and so this should hold over all possible databases because this is the kind of like nature of the privacy guarantee. In the worst case, it could be all of n, and so in some like worst case, maybe I'm like star node and I'm neighbors with like everybody. It turns out that isn't possible, and it depends on the like geometry of the space. And
But the best possible case is replicate. If there were random points with some
in the best possible database, if you say that the
2K or something, right? Because
Yeah.
you use to get each new sample, you use 2 samples.
yeah, if you want to like greater things in some way. But importantly, we care about the worst case database and not about the average case. So this kind of like helps us as we show this as well. Any more questions before on the statement before I explain where it comes from?
go ahead.
Yeah, so the classifier C you're using is like an epsilon DP classifier, right? So like in the definition, you say that if you change 1 point.
You should actually think of it as an epsilon DP learning algorithm that will learn a classifier.
Yeah, so it's more like if you change like 1 point in your initial distribution, like you don't want the output to change by like some epsilon.
Yeah.
So But does it make sense to like, so now if you change like 50 points, like the usual thing would be to say that like the output changes by 50 times epsilon or something.
Yeah.
But does it make sense to consider something that where this does not grow like linearly?
So the math that I didn't talk about here says in fact it does grow linearly. Yeah. And so if you have a precise K, they like together are going to receive like a K times epsilon privacy, where in this case, your like group is the like set of data points that are a function of your data.
You mentioned this result shows that this pipeline performs pretty badly, even though you think it should perform well. So that are these bounds, are these tight? Like a lower bound?
Good. Okay, good. This is 0.5. So like I'm currently no, I conjecture yes up to some like maybe improvements, but I conjecture they are mostly tight. Let me explain things. And I'll say where I think they're not tight. People see if I write like on this thing or on that thing. This one is better. Okay. Should I raise this board halfway? It was taught how this one. Okay, good. It'll like raise block these a little less. Cool. Everyone can see if I'm over here. Okay. So first we'll start. Ooh, nice. Thank you. Okay, that's ooh, even more. Okay.
Yeah,
Okay.
there's only two like
This is fine. Okay. So we'll start with the definition of a C-stable form. And this comes out of like a privacy kind of SQL coding, and so the language doesn't quite match what we do here, but the math does. So it's okay. So say that a transformation T is C-stable if I look at T applied to A, and I look at the set difference between that and T applied to B, then it should be at most C times this this like a difference between A and B. What does this mean? Is we translate it into our language. So you can think of this like, A and B as being like a neighboring databases. And so we know they like differ by 1 point. So we know this equals 1. And we are thinking about like T as SMOTE. And so we're really asking, if I change 1 point to my input database, we have a bound on the maximum number of points that will change in the output of SMOTE across these two things. Okay. So this is our goal. And we also have a theorem that is not ours. Frank McSherry and co-authors in some private SQL paper. I should write this down. It says the composition of first a C-stable T and epsilon DP-M satisfies C times epsilon DP. So I'm thinking of first applying T to my database and then applying M. And so we're saying this is C epsilon DP. Everyone happy? Can you see? If I can push this. Oh, this. Oh, I wrote on the part that doesn't go up. Sorry. I should have planned better. Okay. Okay, good. So we have this. So now let's think about, just stay on this side. Yeah, okay. So our goal is to find a C for which this is true for smoke. And our question is kind of what is our C? And now we want to ask how many points, yeah, so I'm purposely not going to use Y or use C for kind of reasons will become obvious soon. But instead I want to say, let's let Y be the number of points that change between the outputs of smoke on these two neighboring databases, and that's a typo that doesn't belong there. Okay, so let's think about what happens. So yeah, I think this is will come in handy. Okay, good. So let's let Y be number of points differ. I'll let Y be is like absolute difference of like smote on D and smote on D prime. And let's also keep like a randomness fixed here internally. So I'll use the same randomness in both. Okay. So let's think about what happens in a single run of smote. What can happen? So we have a center point and it has k nearest neighbors. And because I'm fixing the randomness, we can think maybe this is the one point that will differ between like D and D prime. And so the bad case is when I have picked a smoke point here. And because now like this point will not happen. So then instead I will pick a different point that is a new neighbor. I don't pick some point here instead. Because of course this happens with like a probability of 1 over k. Like I'm conditioned on the fact that I have a node that is a neighbor. Okay, so we have like success probability k every time a kind of one node that is different is included. And so then like how many times can this point be included? So first I'm going to have LDK. And this counts like of how many times in a single run through my like minority class am I going to have this point to the neighbor, and then it might run through it, capital N over lowercase n. So it tells me Y is just a binomial variable where I have L dk n over n trials. Probability 1 over k. Yes, so far? Okay, good. And so now we have to think about this Y is my C, but my Y is a random variable. How do I cope with that? Well, so there's like one thing that you could do is you could say, well, so then we can say, we can see that like with probability 1, my Y is going to be less than this bound, LDK n over n. And so this tells me this is my C over there. And so then using that theorem gives me L dk capital N over lowercase n 0 dp. And so that's pretty straightforward. But again, we're trying to show smoke is bad. And this is kind of like an unfair characterization of it because we know with high probability, you're not going to observe every single success. And so maybe you can have some like bound on this. Maybe instead you can say, well, I know that y is going to be less than some value of high probability. Minus theta. And so this is our point 4, is we can say actually like I can bound y with high probability. And in this result, we say turnoff bound, these are generally not tight. And so back to yours. Like I suspect it can be improved in the turnoff bound part, but I think that kind of all the rest of the analysis is just like the right analysis, and I hope the lower bound can be done. And so basically what you do is you can say, well, this y is going to be bounded with high probability. And there's some theta that I will suggestively call delta, with which is what will fail. And I can plug this back in over here, and I can say, so with high probability, I will receive the epsilon dp, and there's some failure of that, and that failure is there's an excellent question. Lower bound, I believe it is true modulo details. I'll skip talking about how to bound this thing because I know that we're almost at time. But I will just say you can do this based on some math papers in the 60s, and this was generally where the kind of the magic happens is you find a math paper in the 60s and you're like, this is a God's own truth. So, I'll tell you afterwards. It's really interesting, but I want to end on time. Yeah.
Can I say something else? So this is okay. So the thing is, this is not so great.
Yeah.
Can you combine maybe the preprocessing?
Yeah. Okay. How do I lower this slide again? So good. Okay. So when do we end? In how many minutes do I have left? It's how many slides do I?
I guess.
I was going to skip even more, but that's great that there won't be a riot. Everyone had tacos in they're happy. So yes, so back to this stuff. Okay, so good. And so back to the pipeline question is we could just make a differentially private version of SMOTE, and then our problems are solved, and then because of a composition, then grades, we have an epsilon, we have a second epsilon, we just add them up, and then you have 2 epsilon. So great. We need a differentially private version of SMOTE. And so I think for time, here is where I skip. And the short answer is that we try to do really fancy algorithmic things, and I'll skip through all of these, and you do fancy algorithmic tools and they fail, and then you do fancier algorithmic tools and they fail, and and you're left, oops, and you're left
Doing very
yeah. Sometimes my clicker is not working. I don't know why that's okay. And then you have a sad face. So basically, you try and do fancy things and they all fail, various technical reasons, and then you go back to square one and you're like, what do I do? What if I did a histogram query? And yes, I think the laughter is right. And it turns out this actually works. So you like, take your data and you grid it, and you find the cell centers, and you then just like, compute noisy counts for these cell centers using the like Laplace mechanism, which is where you like, compute the exact count of each cell, and then you add noise. It is mean zero and has variance that like, depends on your epsilon. Is basically like a two-sided exponential distribution. It's like the most common thing in the like a different privacy space, and like no one else uses it. So if you've like seen like a DP before, this is obvious. If you haven't, you're like, oh, why do I want this? This is a weird thing, but you do. So you do this. So you do this first, and you pretend your cell centers are the data, and they have weights equal to the noisy counts as a result of your private query. So again, it's like not algorithmically interesting, but it works. I know the fancier stuff didn't. And you need a slightly different version of like, k nearest neighbors, because you're in a grid, and you can like define a kind of like analogous version in a very natural way. So this is what you do. So you first perform like a DP. You first like perform like, noisy histogram, how you have your like grid and your centers, and you just add like, Laplace noise to the counts, and then you have those counts. And then phase two, then you do SMOTE, and you pretend like your histogram points are the ground truth, and you just like, sample them like proportionally to the weight according to these like, to these kind of noisy counts. And this is like a differential privates. And one important note is that the kind of, as you plug this into the pipeline, you have to be careful. They did this like a pre-processing thing, and so you can't just say the kind of like I did SMOTE and it's private. What happens next is post-processing. That's not true, because like presumably in the like post-processing learning step, you're going to still use like the original data, and so like you will like combine your like the private output with the real data. So you have to be careful. You still have to do like a downstream learning privately, and then it's like 2 epsilon private everything. So let me. So this is for the yeah.
Oh, I have a question. So is the granularity of your histogram grid, does this depend on epsilon, or is it?
Good. So this is a feature of a histogram query, and this is like this point that I skipped. Let me do it in the picture. So we think of this as having as being just like a very long vector. One thing free point. And I then want to ask, how would this like vector change if I changed one point? Well, so this vector like only change in one component. Let's say that I like remove this point. Well, that wouldn't affect any of these counts, in particular because I have like a partition. So this was a solution to the things I skipped, which is like, how do you say I want like a data structure that I can just like sample from arbitrarily without incurring additional privacy loss as a function of the number of points. And so here I don't have to scale my noise based on this like a dimension. And so the alpha term is more just for like computational efficiency. How fine of gridding can your laptop or your server handle? So I'm going to end with just one empirical slide. and I'm happy to like chat more. And it's like this kind of like shows it. So let's say that I want to do like deep learning, and I picked epsilon equals 10, which like by the way isn't a great epsilon, but we just chose it. And so if you're doing DP-SMOTE, then you can just like split it, epsilon equals 5 each half. On the other hand, if you want to account for the fact you're doing SMOTE and then like amplifying sensitivity, then you have to use a kind of like a much smaller epsilon, and this like epsilon equals 0.24 was like based on the specific data set that we used. Like anyways, if you think that you're getting epsilon equals 0.24, you might actually be getting 10. And then like even in this case, DP-SMOTE performs like a much better for the same epsilon. On the other hand, if you don't do this analysis and you think that you're getting the epsilon that you actually get, then they like to perform about the same. So I feel like this is the main point, is that kind of like an epsilon here does not mean total epsilon. So I will end on time, and I will say this, that I think although like I can say we have an algorithm and it works, that's kind of like not the main point. The main point is that if you don't account for what happens in your pre-processing step, you're going to be getting the wrong privacy guarantees, even if you apply like a correct private algorithms later. I will end here, and I'm happy to like have questions, discuss. If anyone has to flee, that's okay.
I had a quick question. So for the original SMOTE algorithm, are there theoretical guarantees on how much it fixes the bias in the data set? And are there guarantees on the DP-SMOTE, like what the trade-off is for the privacy?
Good. In fact, this was one of the slides that I like ambitiously skipped, which is like the answer is no. So they don't have like any theoretical bounds. The paper for like 2002, and I think like before this, everyone just kind of like replicated minority points and were like it's fine. And then they said actually turns out empirically on like 5 different data sets, doing this is better. And that was a big deal. But there was no analysis of the accuracy. So normally when you're doing private analysis, you kind of go through kind of original like a non-private accuracy, and then you look at like how things change when you add noise. And there was 0 accuracy analysis of it. So that's why we did plots instead of groups. Yeah.
So K here is sort of small, but if it seems that somehow, what if K is n over 2 or something? Does it still work, the SMOTE, or?
Oh yeah, so do you mean in terms of accuracy or in terms of these like privacy
The
implications?
privacy gets much better because suddenly simple things, right? Simple things will work again.
Actually, the privacy gets worse because, maybe because
Because you don't affect what
yeah,
other
because you
people are
divide
doing.
by, yeah.
But-
Yeah, there's 2 conflicting effects, and I'm not sure which one would be worse. One is that you will be neighbors of more people, and that's bad. But the other is like a condition on being a neighbor, you have a lower chance of being chosen as a neighbor, and so that's good. So I don't know immediately. Like,
What about performance? Does it suffer a lot?
performance, I don't know. That's a good question. One thing we did find is that like SMOTE works really well when you have data sets. The minority class is very clustered because then you're just sort of like making more points there. If they're kind of like integrated with the majority class and they're like on top of each other, it doesn't help as much because there's like less information about like majority versus minority. So that's
folks.